Right. So now let's talk about the proof by exhaustion method. The proof by exhaustion. Well, exhaustion in math here, what we're doing is we're basically running through every single case analysis, and then we're showing that okay, it's not working. So let's try to approach this problem here, and we're going to identify what are the possible cases for each value, for each situation, and then we're going to show that it's true for every single situation, and therefore it is definitely true for all cases. So let's look at this problem. Given that the n to the power 5 minus n is equal to n minus 1 times n plus 1 times n squared plus 1, prove that n to the power 5 minus n is divisible by 5 for all n. So what kind of situation are we dealing with here? So in order to prove that n to the power 5 minus n is divisible by 5, well, it means that n to the power 5 minus n can be represented as, let's say, a 5k, for example. So it's divisible by 5 in all cases, where k is an integer. Well, because let's try to use the given equation of n to the power 5 minus n is equal to that. So I think we can rewrite that as n minus 1 times n plus 1 times n squared plus 1 is equal to a 5k, or they're divisible by 5. Well, where can we approach from here? Well, we could see that it's for all n. So I think we can put it into multiple cases where n is a multiple of 5, or maybe n plus 1 is a multiple of 5, or n minus 1 is a multiple of 5, and so on. And let's make sure that we meet all the cases here. So let's put it into multiple cases. Case 1, n is divisible by 5. So n is represented. Let's use a different letter here. Maybe n is 5m. So what do I know if n equals 5m? Well, it means that my n minus 1, or my entire equation, can be rewritten as 5m minus 1 times 5m times 5m minus 5m plus 1 times 5m squared plus 1 is equal to 5k. Well, is that true? Well, I think that we can easily factor out a 5 here from the 5m and go like this. 5 times 5m minus 1 times m times 5m plus 1 times 5m squared plus 1. And I think we can easily tell that the expression 5m minus 1 times m times 5m plus 1 times 5m squared plus 1, well, m is an integer. So therefore, that is also an integer. So it must be 5 times an integer is definitely divisible by 5. So yes. So indeed, for n equals 5m, n to the power 5 minus n is divisible by 5. So basically, we're seeing the case where n equals, for example, a 5, where m equals 1. Well, then what other cases can we have? We can have case 2. Let's say we have n equals 5m plus 1. So this means that, for example, we have a number 6. 6 is 5 times 1 plus 1. So let's try. So it means that I can replace every single n with 5m plus 1. So it's going to be now 5m plus 1 minus 1 times 5m plus 1 times 5m plus 1 plus 1 times 5m plus 1 squared plus 1. Well, we can reduce the 5m plus 1 minus 1 into 5m. I think you see where we're going here. What we're doing is, for each case scenario, we're showing that the 5 can be factored out from the expression, and the remaining expression, is definitely a integer, and therefore being able to factor out a 5 shows that it is indeed divisible by 5. So here we can say that for n equals 5m plus 1, power 5 minus n is divisible by 5. And let's keep going. Case 3, where n equals 5m plus 2. For example, we're thinking of a number like 7. Well, let's plug it in. 5m plus 2 minus 1 times 5m plus 2 times 5m plus 3 times, plus 2 plus 1 times 5m plus 2 squared plus 1 equals 5k. Well, I think that even if I simplify the first 3 factors here, I wouldn't get any terms as a multiple of 5. So I think I'll need to touch the last section here. Let's open up. It becomes 5m, not 5m, 25m squared plus 5 times 2 times 2 will be 20m plus 2 squared is 4 plus 1, which, let's rewrite 4 plus 1 is 5, which can be factored out. 5 can be factored out from there. 5m squared plus 4m plus 1. So my entire thing can be rewritten as 5 times 5m plus 1, 5m plus 2, 5m plus 3, and 5m squared for plus 4m plus 1. So same thing, the remaining expression is a integer and 5 as a multiple. So we can say that for n equals 5m plus 2, n to the power 5 minus n is divisible by 5. I think we only have 2 more cases to go. So let's go. Case 4, n equals 5m plus 3. 5m plus 3 minus 1 times 5m plus 3 times 5m plus 3 plus 1 times 5m plus 3 squared plus 1 is equal to 5k. Once again, I think the first 3 factors wouldn't give me a multiple of 5 immediately, but the last factor probably should. 25m squared plus 5 times 3 times 2 is 30m, and then plus 3 squared is 9. 9 plus 1 is 10. So I think we can say that 5 can be factored out from the last factor. Which means that we can represent as 5 times 5m plus 2 times 5m plus 3 times 5m plus 4 times 5m squared plus 6m plus 2 is equal to 5k. So therefore, we know that it's 5 times an integer, so therefore it is divisible by 5. Okay, next case is when n equals 5m plus 4. All right, last one. 5m plus 4 minus 1 times 5m plus 4 times 5m plus 4 plus 1 times 5m plus 4 squared plus 1 equals 5k. So in this case, I think the third factor will become a multiple of 5. I wouldn't bother expanding this one right now because I don't need it. So I think we can factor out a 5 from the 5m plus 5. So finally, we can write this as 5 times 5m plus 3 times 5m plus 4 times m plus 1 times 5m plus 4 squared plus 1 equals 5k. So therefore, for the same reasons, for n equals 5m plus 4, n to the power 5 minus n is divisible by 5. Now, one thing that we realized after doing these case analysis for each case, n equals 5m, n equals 5m plus 1, n equals 5m plus 2, n equals 5m plus 3, n equals 5m plus 4, maybe you can think of, oh, what about n equals 5m plus 5, the sixth case? Well, 5m plus 5 can be factored out as 5 times n plus 1, but then that's the same thing as the case 1. 5 times an integer. Integer plus 1 is just the same integer. So we know that we have covered every single possible scenario of n where m is an integer and 5m plus 1, 5m plus 2, 5m plus 3, 5m plus 4 covers every single possible integer of n. So therefore we know that the proposition is true. For all cases of n proven by exhaustion. So once again, the word exhaustion kind of makes sense after doing all the cases. We exhausted every single possible case scenario for the proposition, and then we have proven every single possible case. Therefore, this proposition is true for every single possible case.